All right. Okay. Just to continue the previous example, this slide extends the system modeling by introducing the additional network components and outlining the steps required to develop a complete per unit reactance diagram. So transformer T2 is modeled as a bank of three single-phase units, each rated at 127 to over 13.2 kilovolt and 100 megavolt amp with a leakage reactance of 10%. Okay, this configuration is typical in HV systems and must be carefully represented to ensure accurate impedance transformation between voltage levels. So the transmission line also is characterized by a series reactance of 0.5 ohm per kilometer, which must be converted into per unit based on the selected system base values and the line length. So the key task in this slide is to construct the reactance diagram where all system components, including motors, transformers, and transmission lines, are expressed in a unified per unit system. So this significantly simplifies analysis, especially for fault calculations and stability studies by normalizing quantities across different voltage levels. And finally, this slide emphasizes the importance of selecting the generator rating as the base in the generator circuit. So this choose ensures consistency in per unit calculations and facilitates accurate components of electrical quantities throughout the networks. All right. So this slide focus on establishing consistent base values for per unit analysis across the entire power system. So first, transformer T2, which is composed of three single-phase unit, is converted into an equivalent three-phase rating, since each unit is rated at 100 MVA. So the total three-phase capacity will be 300 kVA. So um, and next, the line-to-line voltage ratio is derived by converting from phase voltage to line voltage using the escort tree relationship, and it can yield these equations. All right. So we will have this one. So with these values, a system-wide base is selected as a 300 MVA. So sorry, there is a typo here. So this is a MVA, not KVA. So throughout the network, ensuring consistency in per unit calculations, and based on transformer T1's rating of 230 volt per 20 kilovolt, the voltage base in the transmission line is set to be 230. So did you remember all of this is based on the power system one? So and after that we just need to use this relationship to find the voltage base in the motor circuit. So it will be equal to 13.8. So in overall, this slide demonstrates how proper base selection and voltage scaling across transformers are essential steps for building an accurate and consistent per unit system model. So according to the power system one. All Correct. This slide explain how to convert the reactances of system components into a common per unit base, which is essential for simplifying power system analysis. First, the reactance of transformer T1 is adjust based on the new base power, showing how impedance scales with the ratio of base MVA. So resulting in a value of 0.0857 per unit. For transformer T2, the conversion involves both voltage and power base changes. So did you remember we need this relationship to just convert the if the SF base or V base has been changed. So and finally next uh, the base impedance of transmission line can be calculated using the standard relationship. Z base is equal to V base power 2 divided by S base, resulting in 176.3 ohm. Okay, this base impedance is then used to convert the actual line reactance into per unit form. So by dividing the physical reactance divided from the line data by the base impedance, the per unit reactance of the line is can be obtained as 0.1815 per unit. In overall, this slide highlight the importance of expressing all system components on a common base, allowing for consistent comparison and easier network analysis, especially when dealing with transformers operating at different voltage levels. Okay, this slide complete the per unit conversion by incorporating the subtransient reactances of the motors and presenting the final reactance diagram of the system. The subtransient reactance XD zegons of each motor is converted to the common base using both power and voltage scaling factors. We can use this relationship. For motor M1, the base power changes from 200 to MVA to 300 MVA, so we need to multiply to this, and the voltage base adjustment can be applied here, resulting in a reactance of the 0.2745 per unit. So similarly, motor M2, originally rated at 100 MVA, is converted to the same base, yielding the higher reactance of 0.5490 per unit. And this value, which is um, reflected, it's a smaller rating relative to the system base. And the lower part of the slide shows the complete single line diagram, and where all component generators, transformers, transmission line, and motors are represented by their per unit reactances. Each element is modeled as a purely reactive impedance indicated by Jx, which is a standard assumption in short circuit and fault analysis. The generator is represented with its internal voltage and reactance, while the motors are also shown with their internal voltages and subtransient reactances. And the unifying per unit reactance diagram is extremely useful, as you definitely know, because it allows the entire power system to be analyzed using a single consistent framework, regardless of differing voltage levels or equipment ratings and so on. So it can forms the basis for calculating fault currents, voltage drops, and system stability under transient conditions. All right, this slide introduces the task of constructing the negative sequence network for the given power system. In symmetrical component analysis, the negative sequence network represents how the system behaves under unbalanced conditions such as a line-to-line or double line-to-ground fault. Unlike the positive sequence network, there are no internal voltage sources in the negative sequence model. All generators and motors are represented only by their negative sequence impedances. So the key assumption in this slide is that the negative sequence reactance of each machine is equal to its subtransient reactance. X2 is equal to xd zegon. This is a common and practical approximation used in fault analysis because the subtransient period dominates immediately after fault occurs. So therefore, the values previously calculated for the subtransient reactances of the generator and motors can be directly used in building the negative sequence network. So to construct the network, the system configuration remains identical to the original single line diagram, but all voltage sources are removed and each component is replaced by its corresponding negative sequence reactances in per unit. So, and also additionally, transformers and transmission line typically have the same reactance in both positive and negative sequence networks. So their previously calculated per unit values also can be reused here. So the result is simplified but powerful equivalent circuit that can be used to analyze unbalanced fault currents and system response. All right, this slide present both the single line diagram and its corresponding reactance diagram for a power system under study. In the top diagram, the single line diagram is showing the overall structure of the system, including generator, transformer T1 and T2, transmission lines and motors operating at different voltage levels, 20 kilovolt to 130 kilovolt and 13.8 kilovolt. Uh, This simplified representation also help us understand how power flows from the source through transformers and transmission lines to the loads. In the lower, in the bottom diagram, the same system is converted into a reactance diagram using per unit values, which significantly simplifies analysis. Each component, generators, transformers, transmission lines, and motors is represented by its equivalent reactance. It means all of these reactances here in the figure. So the generators and motors are modeled as internal voltage sources behind their respective reactances. These transformations allow us to ignore actual voltage levels and focus on relative impedance values, making fault analysis and stability calculations much more manageable. So in overall, the slide demonstrates the essential steps of moving from a physical system representation to an analytical model suitable for power system studies. All right. This slide also is showing the negative sequence network of the same power system, which is essential for analyzing unbalanced fault such as line-to-line or double line-to-ground faults. In this representation, all components are modeled using their negative sequence reactances, and the system is simplified by omitting resistances and any phase shifts introduced by transformer conditions. So this assumption is commonly made because reactance dominates system behavior during fault conditions, allowing for more straightforward analysis. So the diagram retains the same topology as the original system with buses labeled from K through to N, So just uh, buses has been labeled and include the series reactances of transmission lines as well as the machine reactances. All of reactances has been included here in this diagram. Unlike the positive sequence network, there are no internal voltage sources shown, since in the negative sequence network, sources are typically set to 0. So all of elements are referenced to a common grounded indicated at the bottom, which serves as the reference nodes for the network. Overall, this slide demonstrates how the system is adapted into its negative sequence equivalent to facilitate the calculation of fault currents under unbalanced operating conditions. All right, this slide highlights key concepts related to the zero sequence network in power system analysis, which is particularly important when studying ground faults. So first, it explains that zero sequence equivalent circuits for individual components such as generators, transformers, and transmission lines can be developed separately and then combined to form the complex zero sequence network of the system. So this modular approach simplifies the modeling process. A crucial point emphasized here is that zero sequence currents can only flow if there is a complete return path, typically through the earth or natural connections. We already discussed all of this, just this slide is refreshing your mind. So without such a path, zero sequence currents cannot circulate, which directly affects fault current calculations. The slide also points out that because these currents may flow through the ground does not necessarily remain at the same electrical potential everywhere. So as a result, the reference node in the zero sequence network cannot be assumed to be at a uniform ground potentials. And this is an important distinction from other sequence networks and must be carefully considered when analyzing ground fault conditions. So this slide, for example, will be one of your multi-choice questions, So you will have some multi-choice questions in your midterm exam. So, all right. This slide illustrates a single line diagram of a small power system along with its corresponding zero sequence network, which is essential for analyzing unbalanced faults, such as single line to ground faults. In the upper part of the figure, the, uh, the, the physical system is shown, including generators, transformers with different winding configuration, delta star and Y star. Sorry. Y star transmission lines and grounding through an impedance ZN. The transformer connections play a crucial role in determining whether a zero sequence current can pass through the systems, as delta windings can block or circulate these currents internally, while grounded WYE connections, star delta connections, provide a path to ground. So let me just go to the animation. Okay. All right. So in this slide, just continues the analysis of the same small power system by focusing on how the zero sequence network is can be physically interpreted and constructed step by step. So the in the uh, in the bottom single line diagram, you can see that the corresponding zero sequence equivalent circuit is clearly drawn in this figure, and each element of the original system is replaced by its zero sequence impedance, and the network is a reference to ground. The grounding impedance appears as 3 times its original value, reflecting the fact that zero sequence currents in all 3 phases return through the natural. Additionally, buses that are not effectively grounded or are isolated by delta windings appear as open circuit in the zero sequence networks, and this representation is particularly useful for fault analysis, as it allows you to determine the path and magnitude of ground fault current with greater clarity, highlighting the strong dependence of the zero sequence behavior on transformer connections and grounding practice. Okay, this slide also presents a more advanced example where the objective is to systematically draw the zero sequence network for the given small power system. This figure, single line diagram, shows the multi-bus system with several transformers, with each having different winding configuration, delta star and star star, along with multiple grounding points. The key challenges here is to identify how zero sequence currents can propagate through each section of the system, as similar to the previous network, grounded star-star connection provide a return path for zero sequence currents, while delta windings either block these currents from passing between the buses or allow them to circulate only locally within the transformer. Okay, this slide present the single line of a small power system along the previous small power system, along with its corresponding zero sequence network, which is essential for analyzing unbalanced faults such as single line to ground fault. The above part of the figure shows the actual system configuration, similar to the previous slide, including generator, transformers with different winding conditions, and so on. Each component's grounding and connection types plays a critical role in determining whether zero sequence current can flow or not. The the lower part illustrate the derived zero sequence network, where the system is simplified by replacing each element with its zero sequence equivalent. In this network, only paths that allow zero sequence currents, typically those involving grounded naturals or delta windings, are retained, and the reference ground is clearly indicated, emphasizing its importance in zero sequence analysis. This representation enables you to systemically study fault behavior and calculate fault currents by isolating the zero sequence components of the systems. All right. This slide explains the fundamental concept of analyzing unsymmetrical faults in the power system using the method of symmetrical components. When a fault occurs, the system becomes unbalanced, and the resulting currents can be decomposed into three balanced sets known as zero, positive, and negative sequence components. To evaluate the impact of such faults, it is necessary to determine the corresponding sequence impedances of system elements and construct separate sequence networks for each component. So these networks carry the respective sequence currents denoted as IA0, IA1, and IA2. Finally, depending on the type of faults under study, the sequence networks are interconnected in a specific manner to accurately model the system behavior and enable the calculation of the fault current and voltages. Okay, this slide introduces the process of constructing the zero sequence network for the power system presented in example 6.1. The single diagram shows the generator connected through transformer T1 to a high voltage transmission line, which in turn is connected via transformer T2 to two motors. To develop the zero sequence network, it is necessary to consider the zero sequence reactances of all components and the grounding conditions of each element. The slide specifies that the generator motors have zero sequence reactances of 0.05 per unit, while current limiting reactors of 0.4 ohm are installed in the naturals of the generator and the larger motor, affecting the flow of zero sequence currents. Additionally, the transmission line contributes zero sequence reactance of 1.5 ohm per kilometer, which must be included based on its length. By combining these parameters and carefully accounting for transformer connections and grounding paths, the complex zero sequence equivalent network can be also constructed, enabling accurate analysis of ground fault conditions in the systems. So let me go to the solution. This slide focuses on determining the zero sequence reactances of transformers, generators, and motors in per unit values, which are essential for fault analysis, especially under unbalanced conditions. So first, the zero sequence reactances of the transformers are given directly as x01 is equal to 0.0857 per unit, and x02 is equal to 0.0915 per unit. Then the zero sequence reactance of the generator is specified as x0 is equal to 0.05 per unit. For the motors, however, their reactances must be converted to a common base using the per unit transformation formula. For motor 1, the reactance is a scale considering both power and voltage base changes, resulting in x0 is equal to 0.0686 per unit. Similarly, for motor 2, applying the same conversion approach but with a different power rating leads to higher values. So we will have this value. Overall, this slide demonstrates how zero sequence reactances are either given or properly converted to a unified base, ensuring consistency for subsequent system analysis such as fault calculations. All right, this slide explain how base impedance values are calculated for both the generator and motor circuits, and how these are then used to express the natural grounding impedance in per unit form. In the generator circuit, the base impedance is determined using the relationship like this: Z base is equal to V power 2 over 3 S, which gives a value of 1.333 ohm. Similarly, for the motor circuit, using its corresponding base voltage results in a base impedance of 0.635 ohm. So these base values are essential for converting actual impedances into the per unit system. The slide then proceeds to calculate the equivalent natural impedance in the zero sequence network represented as 3Zn. For the generator, substituting the given natural impedance and dividing by the base impedance, we can find this value, 0.9 per unit. So in contrast, for the motor, due to the smaller base impedance, the same natural impedance results in a higher per unit value. You can see, you can compare these two values. So overall, this slide highlights the importance of consistent base selection and demonstrate how physical impedances are normalized into per unit values for accurate system analysis, particularly in zero sequence networks. Okay, this is a final slide. Complete the zero sequence modeling by calculating the transmission line reactance and assembling the full zero sequence network. First, the zero sequence impedance of the transmission line is converted into per unit using the given base values, resulting in Z0 is equal to 0.544.5 per unit. This value reflects the line's behavior under unbalanced fault conditions where zero sequence currents flow through the ground returns path. The slide then presents the complete zero sequence network diagram. On the left side, the generator is represented with its zero sequence reactance J 0.05 in series with the grounding impedance is equal to this value. Moving along the network, the transformer reactances J 0.0857 and J 0 um, uh, 0915, as well as the transmission line reactance, this one, are connected in series together, forming the path between the generator and motor buses. On the right hand side, the motors are modeled with their respective zero sequence reactances. We have these two zero sequences as we calculated in the previous slide, along with the grounding impedances, so which is equal to J 1.890 for motor 1. Overall, this slide illustrates how all previously calculated zero sequence components are integrated into a single equivalent network, and this network is essential for analyzing ground faults as it provides the complete path for zero sequence currents and enable accurate fault current calculations. All right. Thank you so much for your attention. Let me just